Okay, everyone, let's get started. Good morning. How's everyone feeling? Good? So I'm going to start out, I'm going to review what we talked about on Thursday, and then I'm going to try to get us up to the point where we can start Lab 1 on Thursday. Okay. So last time we talked about hardware-software interfacing, and from the software perspective, which is like as a programmer who's writing a Linux driver, the way that you talk to hardware is through three mechanisms. There's programmed I/O, which is where you basically just use load and store instructions as special I/O address ranges. When I say I/O address ranges, I mean the effective address of the load or store would fall in between these special magic ranges that correspond not to memory but to hardware devices. And then you use that to read status registers and write control registers, which are basically just words that you pull out or send to the peripheral that have different meanings and have different functions depending on what the user guide says for that specific peripheral. And generally speaking, those registers are divided into fields, and you're usually bit twiddling within those fields. So basically, programmed I/O is a way that the CPU can initiate communication with peripherals by reading or writing to peripherals. The peripherals just have to respond, because in that model, the CPU is the master, the peripherals are the slaves. So you basically initiate either a read or write from the CPU side, and then the peripherals are expected to comply with that transaction, right? And then we talked about interrupts. I mentioned those briefly. That's a way for the peripheral to get the CPU's attention, and that's used for things like when you have a packet arrive on a network interface, or some event occurs where the peripheral needs to get the CPU's attention. And then you might say, well, okay, what happens when it gets the CPU's attention? Well, then generally it's going to use programmed I/O to figure out what's going on and to respond to that interrupt, right? So basically you have an interrupt. It's a wire that goes back to the CPU. It's a signal, usually basically you think of it as a single bit. Sometimes it's more than one bit, but it's essentially a signal that's sent back to the CPU from the peripheral. It causes the CPU to automatically go into the driver, at which point it starts doing programmed I/O to figure out what's going on and how to service that interrupt, okay? And then direct memory access is used for high-speed I/O, which is where you're doing high-speed blocks of data transfer between a peripheral and memory. That's used for hard drives and display adapters. You're not going to find DMA in a lightweight embedded system like an Arduino. They are in Raspberry Pis, but you're not going to find that in an Arduino. It's only for, that's a high performance mechanism, okay? So like I said, these haven't changed in decades. These are the three basic mechanisms that the software uses to talk to hardware, but that's from the software perspective. From the hardware perspective, we have these various I/O protocols that no software is involved. In this case, you're looking at a timing diagram. So you start getting to hardware design, and when you do hardware design, you're not looking at code so much as a timeline of bit switches over time, right? And that's what we're going to be looking at as we examine these I/O standards, is reading timing diagrams, as opposed to looking at software or arithmetic expressions or concepts like that. Okay, so this was the programmed I/O. So in this case, we had different peripherals. Now this might come off as a little confusing. I just want to clarify this. So in this picture, the gray part is a chip, represents a chip. On that chip, we have a CPU, we have an interconnect. The interconnect's purpose is to allow one load and store, one load store interface, one memory interface from the CPU core to get, splayed out into multiple endpoint connections on there, okay? And then the interconnect actually has knowledge of these I/O address ranges. How? It's like hard-coded in there somehow, right? You actually burn this into the hardware, right? So the hardware, this interconnect knows what these I/O address ranges are, uses those to route these requests to the appropriate endpoint, right? The load or store request, programmed I/O, read and write. And then the peripherals, in this case, these peripherals are actually off-chip, well, most of them, 3 out of the 4, are off-chip interfaces. So the CPU would talk to this USB peripheral using programmed I/O, right, as I described, but then it would then go off-chip with a USB bus off-chip to talk to an off-chip peripheral. So this thing is a bridge, basically. What it's doing is it's bridging this programmed I/O interface between the CPU and this circuit with the USB interface that then goes off-chip, right? So this is kind of like a a transceiver. Think of it like a transceiver. And so like on a cell phone chip, you'll have, you'll literally have a radio transceiver, you'll have a USB, interface. These are all things that allow the CPU. So the CPU treats them as little slaves on the chip, but then they act as the interface to then go off chip, right, and talk. In some cases though, like this timer doesn't do that. The timer is entirely contained on chip, and it's just a hardware timer. It's like looking at a clock, basically, right? It allows you to synchronize things going on in the CPU, and timers are useful whenever you have to synchronize the software with the real universe as it moves forward in time, right? So this is used for real-time style operations where the software has to trigger every so often in order to update the cruise control system or the robot actuators or the temperature, or whatever, right? The valves in a factory. So but these are just examples, right? But these are the kind of things you see on our Arduino. We kind of modeled this picture after the Atmel 328P chip. Okay, so then we talked about bit twiddling. When we first started teaching this class, I thought we didn't really cover this very heavily because we kind of assumed everyone would be okay with this, but then I realized that they didn't really cover this stuff very well in our earlier classes. That's why we emphasize this so much now. So if you're wondering where all this came from, it was kind of an answer to some confusion we had in the past when we kind of just blew through this. But the bit twiddling thing is essentially about doing shifts and bitwise logical operations in order to manipulate individual bits. And that's kind of the irony, is that in an instruction set architecture, you can do a 32-bit multiply with one instruction, which is vastly more complex than just setting bit 2, right? But yet, setting bit 2 requires 12 instructions to do it. It's kind of weird, right, when you think about it. It's odd, right? There ought to be just an instruction for doing that, but I've never seen an architecture that had one. So essentially, you have to go through several steps. The point of this is you have to go through several steps to do things like extract a bit field from the middle of a register or to set a bit field in the middle of the register. And whenever you do programmed I/O, you do a lot of that because control and status registers are usually divvied up into bit fields where you have to grab and set those bit fields. Make sense? Okay. So I went through those. Was there any questions about this stuff? Okay. Okay, so then I summarize stuff there. Then I talk about load or store in C. Loading and storing in C is a dereference operation, so it's basically star. If the star is on the right-hand side, it's a load. If it's on the left-hand side, it's a store. But sometimes you have to use these intrinsics instead, which are explicit ways to do I/O reads or I/O writes using a macro. Or an intrinsic is a word that means it's like a function call or a macro, but if you call it an intrinsic, it means that it maps specifically to one hardware instruction, right? And so this would map to one hardware instruction. Although technically, when you put the address in there, it may expand. There might be several instructions generated to compute that address, right? To calculate that address. But basically, the I/O write this is on the FPGAs now, and this example comes from the FPGAs, or the processor on the FPGAs, the Neos 2 processor that you guys all used in 313. In that processor, the I/O write 32 corresponds to the store I/O instruction, STIO. Okay. And again, the purpose of that is to bypass the cache, if there's a cache. Okay. Let's see. So I went through some examples, example questions. Okay. So let's talk. There's a couple things I want to address here quickly before we get into the larger topic. So I want to talk about pulse width modulation, interrupts, and then we're going to launch into the SPI protocol, which is a much longer topic. Okay, so we're going to jump around here a little bit. So pulse width modulation is a real simple concept. It's a way for a relatively inexpensive processor that just has digital I/O to effectively have an analog output. And the way it works is instead of having a digital to analog converter, in which that's actually an analog circuit that takes a digital input and actually converts it to an actual analog signal. Pulse width modulation is a way to cheat and not have to pay for that by essentially using a digital pin. A digital pin is just 1 or 0 or ground or whatever your power supply is, and essentially making it into sort of a clock signal, a periodic signal that switches, like that continuously switches between high and low. But that signal has a duty cycle, which is the percentage of the period that the signal is high, which is set to be a percentage of the VDD value, right? So in other words, to describe that, is a PWM is basically a periodic signal that has a frequency, has a switching frequency, or a period, which is the repetition length, right? The length of the repetition, or the length of the repeating pattern, right? The period. And the percentage of time that the signal is high within that period is effectively can be multiplied against the VDD voltage, and that will look like the analog value over long stretches of time, right? So in other words, let me show you that. Okay, so here's an example where you have this is a periodic signal, which it just switches between 1 and 0, right? And the period can be measured from rising edge to rising edge, for instance, right? Or from falling edge to falling edge. So that's the period. And the period is just repeated, forever. And then within each period, you have a time where the signal is high, a time when the signal is low. The percentage of that period that the signal is high is called the duty cycle, right? And so if you take a PWM signal, and let's say that your high voltage is 5 volts, and let's say your duty cycle is 50%, if you take that and you put it into a low-pass filter, in other words, you filter out these sharp edges, it'll effectively look like a 2.5 volt signal, because it's essentially a repeating signal between 0 and 5 volts that's high, that's 5 volts 50% of the time and is 0 50% of the time. So over time it looks like a 2.5 volt signal, right? And this is how, this is used a lot. This is used to control motors, power electronic, voltage converters, voltage regulators, inverters, AC, DC, DC, AC converters, all that stuff. It controls DC motors, it controls brushless motors. It's used also for audio. So if you've ever heard of a Class D amplifier, audio amplifier, these are the kinds that you would have, like, for example, PA system or something like that, amplifies someone's voice. Those usually use this, although they're combined with a low-pass filter on the output. But essentially, they use this switching technique to essentially take a digital signal and make it analog, right? So this comes up a lot, but the concept is very simple. A 0% duty cycle would just be a 0, and a 100% duty cycle would be, for example, 5 volts if this was a 5 volt signal, and a 10% duty cycle would be 10% of 5 volts, right? So it would be 500 millivolts, right? Does that make sense? So we're actually going to use this in 3 of the projects in this class. That's how important I think it is. In lab 2, we're gonna generate this using software. In lab 3, we're gonna generate this using hardware. In lab 4, we're gonna use this to control a motor, right? So but there's really not much else to say about PWM. It's a pretty simple idea. Now you might say, well, wait, hold on. You explained how you define the duty cycle, right? The duty cycle is essentially the analog value, right? Whatever analog value you want to put out, that's how you pick the duty cycle. How do you pick the frequency? The frequency is, that's a harder decision. So the frequency depends on the application. Generally speaking, you want the frequency to be as high as possible. Usually, if you buy an Arduino, an Atmel, 328. When I say Arduino, I mean the quintessential Arduino chip, the 8-bit Arduino Atmel 328P. That has a hardware PWM circuit on it. It's part of the timer peripheral. And I think it runs at 25 kilohertz. So that's generally where you'll see a lot of PWM signals work at. Now, if you get into power electronics and you start getting into these solid state power electronics devices, like they're transistors, MOSFETs, but they put them in silicon carbide or gallium nitride semiconductor material, and or IGBTs, which is kind of the earlier technology, which is a kind of a hybrid between a MOSFET and a bipolar transistor. Those ones, depending on how aggressive your power electronic technology is, usually the more aggressive ones require higher switching frequencies. And usually that means you're going higher voltage with the power electronics. Higher voltage means higher frequency. So if you go to a Tesla, for instance, and you look at the power electronics in a Tesla, you're going to see you're going to see a lot of PWM things in there, and they're generally going to run at possibly up around megahertz, right? Because they're higher frequency. But the frequency is a little bit more nebulous, how you pick that. Usually with embedded systems like the one that we're using in class, you'll use whatever the hardware allows, whatever it's kind of hard set up for, right? If you're designing your own PWM circuit, then you can make your own choice. In this class, we're using an FPGA that has a 50 megahertz clock, right? And so we're going to build our PWM built from a 50 megahertz clock. And so we're going to have a little bit of flexibility in choosing what our frequency is. If you're using a PWM signal to brighten or dim an LED light, for instance, and you choose a frequency that's too low, you'll see flickering. You'll see the light flickering, and it looks kind of bad, right? So if you don't want that flickering, that weird flickering effect, you just crank up your frequency on your PWM, and you get a nice dimming effect on your LEDs, right? And this is how, of course, LEDs are dimmed, generally speaking. Again, it's a PWM signal. So, you know, everything from lights inside a car to, you know, your charging light on your MacBook, they're all PWM control. Any questions about that? Okay, there's not much else to say about PWM. So here's an example question. What analog voltage is generated from a 3.3 volt PWM signal having a 30% duty cycle? It's basically 3.3 times 0.3, which is 0.99, right? Okay, so switching topics again, interrupts. I mentioned interrupts briefly. Interrupts are, as I mentioned, it is a signal that's sent from a peripheral to the CPU. It's the only way a peripheral can really initiate communication with a CPU. Because otherwise, generally speaking, in a computer, the CPU is always the master. It controls everything. And if you have an accelerator, like a GPU or a TPU or a neural processor, those are all essentially peripherals too. So, you know, in this day and age, if you look at like a phone, an embedded system like a phone or a tablet, or even really desktop CPUs, the processor doesn't do a whole lot anymore. The actual CPU, it really just farms out work to co-processors these days, right? At least in terms of, you know, whenever you're doing computer vision or machine learning or Face ID or animojis or motion tracking or anything like that, anything that's like computationally intensive, the CPU doesn't do that because CPUs haven't gotten any faster for 20 years. So the CPU really just kind of farms work out to peripherals and manages I/O and runs the operating system, but generally speaking, it doesn't do a lot of heavy lifting computationally. It uses these programmed I/O things to just kind of tell the special circuits what to do. Anyway, so interrupt is the way that the peripheral signals back to the CPU. This could be a keystroke, a network packet, a DMA transfer may have completed, and you got to tell the CPU, okay, it's done. I loaded the data from the file into memory. What do you want to do with it? So those are interrupts. I think in 313, you guys probably connected the interrupt for example, from the UART controller back to the CPU when you guys did it in Platform Designer, but you didn't actually use the interrupt for anything because all the console I/O you guys do in 313 is just output. But that interrupt that you guys connected would have been a way, for example, that you could have written a program on the FPGA that would have said press any key to continue, and you hit a key and it would continue. That interrupt would have signaled that keystroke, right? Okay, so I think Okay, so how does an interrupt physically look? So the simplest way an interrupt would work would be a single wire from the peripheral to the CPU, right? So you have a wire that's normally logic 0, and a logic 1 on that wire would be, hey, I need your attention, right? At which point the peripheral would expect the CPU to automatically execute an interrupt service routine on behalf of that peripheral, right? And then finish. So the CPU is sort of acting like a server in a way, and the peripheral says, I need you to service me, right? So it triggers the interrupt. Now there's a problem with this approach though, because the peripheral doesn't know how long it's going to take between when it raises the interrupt to when the ISR starts. Because the CPU might be busy. The CPU might say, because interrupts are prioritized. So if the CPU is working on something else in the operating system, it may ignore the interrupt for a while. right? So there is a latency here between when the interrupt is raised and when the CPU services it, and that latency is non-deterministic. There's no way for the peripheral to know how long that's going to take. Likewise, the peripheral doesn't even know how long it's going to take to run the interrupt service routine, right? Who knows? Maybe the CPU generates a page fault or something, or or maybe there's, like with Linux, there's queued interrupts, so you can have several pending interrupts at one time, right? So this is also non-deterministic, right? So the problem is that the basic problem here is that the peripheral doesn't know how long to hold that high. It doesn't know how long to hold it high, but it just has to guess, right? Now, if you have a simple system like the Atmel 328, that's the Arduino, that's exactly how it works. The peripherals in the Arduino just kind of have to guess on this stuff, right? Not a great system. And it leaves some problems here that can happen. So for example, well, first of all, before I get into that, I also mentioned that there are two types of ways that this signal can be interpreted. It can be level sensitive, meaning that the CPU is responding to the level when it's high, right? Or it can be an edge sensitive, where the CPU sees the rising edge from the transition from low to high, right? So that just depends on the hardware. Yes?
Is the ISR just like a cycle of checking interrupts?
No, it's more than that. It's the ISR, depending on which peripheral it is. The ISR usually is a sequence of programmed I/O operations that service. So the interrupt goes high, and the first thing the CPU does once it gets into the ISR is it has to pull the peripheral and say, it'll have to pull a status register down and say, what's going on, man? Why'd you interrupt me? And then through that status register, it'll know what the problem is. Sometimes it has to check sometimes there's another register called the cause register. I don't know, the MIPS architecture had a cause register. You probably didn't cover that in 212, that's kind of esoteric, but in the MIPS, there was a cause register that the first thing you checked was the cause, which was a code for which peripheral actually requested the interrupt. Then, once you know that, then you have to go and branch off to another interrupt service routine for that specific peripheral, and then do a programmed I/O on it to figure out what it needs, and then do whatever. So it really depends on what the hardware is. Yes?
So are we just going to write like a little interrupt handler function and then have that jump whenever an interrupt?
Yeah, that's generally how you do it. I don't think we actually have. This is more of a concept thing. I don't think we're going to use interrupts in our project. But yeah, that's what you would do. You'd write it. You can do that on the NEOS, in the FPGA. You can write your own interrupt service routines, and then you register them with the HAL, the hardware abstraction layer.
You can do it even in assembly, just the way you load certain values into register and then call that interrupt, and you can do it even on PC with assembly language. So.
Okay, so here's a question. Suppose a peripheral is connected to the CPU's external interrupt input. Assume the peripheral can change the value of the external interrupt no more frequently than every 50 microseconds. So basically, if the this is assuming the peripheral wants to toggle its interrupt as fast as possible, then it can toggle it every 50 microseconds. Assume the CPU can execute its interrupt service routine in 75 microseconds. What's the maximum number of interrupts per second possible when using rising edge trigger interrupts or level sensitive interrupts? Okay, so with rising edge level interrupts, if you can toggle the interrupt every 50 microseconds, then the time between rising edges would be 100 microseconds, because you'd have to toggle it up, toggle it down, toggle it back up again, right? So you'd have to toggle it twice in order to get two of the same edges, rising edges, right? Rising transitions. So basically with edge triggered, you're limited to 100 microseconds per interrupt, right? And from the peripheral's perspective, right? And then the frequency would be the reciprocal of that, right? In the case of level sensitive interrupts, it would be this. Well, with level sensitive interrupts, you could just set it high and leave it high, right, indefinitely, and then it would just continuously re-trigger, right? So in the case of level sensitive interrupts, you wouldn't be limited by the the rate at which you can change the interrupt wire, you would be limited by the rate at which you can execute the ISRs. So if it were level sensitive, you could basically set the interrupt high, and then you could essentially live lock the CPU by making it continuously service that interrupt, consecutively over and over again, at which point you could do one every 75 microseconds. So the rate at which it would execute interrupts would be 1 over 75 microseconds, right? Whereas with edge sensitive, you would be limited not by the ISR time, you'd be limited by the fact that you could only get a rising edge every 100 microseconds. Make sense? So basically for edge triggered, it would be the minimum frequency between 1 over 75, right, which would be the minimum, and 1 over 50, right? So actually I think I screwed that up. That should be level sensitive, right? If it's level sensitive, we're choosing between what is slower, between the rate at which, what's the slower rate, right? The 1 over 75 microseconds or 1 over 50, right? Or actually, that would just be, like I said, you could just keep it high. So anyway, the answer here would be, 1 over 75, which is 13 kilohertz. And then in the case of edge sensitive, so again, I have these swapped, I'll fix that. It would be, the limit would be 100 microseconds, as I mentioned. So that would be 10 kilohertz, right? So in other words, if you're using level sensitive, you could execute interrupt at a rate of 13 kilohertz. The limit there would be the 75. And if it were edge sensitive, you'd be limited to 10 kilohertz, and the limit there would be the toggling rate of the wire, right? Okay, so so you might be thinking then, well, that creates some issues here because what happens if I keep that interrupt signal high for too long? Like let's say it's level sensitive, right? And I set the level high, and I keep it high a little bit too long. If I keep it long for longer than it takes to both initiate and run the ISR, then I might accidentally trigger 2 ISRs when I didn't mean to, right? Because the problem here is that the peripheral has no idea when the ISR starts and when it ends, right? Because there's no handshaking. Obviously, it's only one-way communication. And then, likewise, you could have another situation arise where, in this case, edge, if you're doing edge triggered, for example, I could trigger an edge here that'll start the ISR, but if that takes too long, then I may try to trigger a second interrupt before the first one's done being serviced, in which case the second one gets ignored by the CPU, right? So there's 2 issues here, is that I may accidentally trigger too many interrupts on the CPU, or the CPU may miss one, right? That's the issue with that scheme. So a way to fix that is to have an acknowledgement that comes back from the CPU to the peripheral. Now, this depends on the CPU. So as I mentioned, the Atmel chip does not have this. But the Neos processor that you guys use in 313 does have this. It has an acknowledgement mechanism. So basically, what happens there is you get this handshake where the interrupt gets initiated by the peripheral, and the CPU will raise the acknowledgement when the ISR begins running, right? And it will lower the acknowledgement when the ISR ends running. So that tells the peripheral, when it can lower the interrupt signal, because basically it'll lower the interrupt signal after it sees the acknowledgement, right? And it won't raise, hold on, let me see, do I got the sequence right? So it raises it here. The interrupt the interrupt service routine is started on the CPU here. Then the acknowledgement goes high here, which then allows it to drop its interrupt request here, right? And then the acknowledgement will go low after the ISR is finished, so then the peripheral knows that it can't send another interrupt until that acknowledge goes low, right? So in other words, this allows the peripheral to know when the ISR starts and when it ends, right? Which tells it 2 pieces of information. 1, when to drop its interrupt signal, and 2, how long before it can issue another interrupt signal, right? Okay, all right. So that's all I've got for interrupts. So those were the two the two quick topics. Now let me talk about from the hardware perspective now. So I talked last time about interface protocols, how hardware communicates. There's a lot of different ways to do hardware communication, and a lot of that depends on basically how long the channel is. So you have one type of communication that happens like between peripherals on a chip, where it's happening over millimeters, and then another type of a set of communication protocols that happen within, like on a circuit board between chips. And then you have another type that happened within modules in a computer, like that go across edge connectors and PCI connectors and go from board to board, right? And then you have other types of protocols that go between computers, like on a network, like through network cables, right? So the distance that the signals are traveling plays a big part of this. Another is the speed that you expect to achieve, how fast you want them to run. So you have some protocols like UART, for instance, that generally don't go very far, but they're simple and they're low cost, right? And they're used just for console I/O, so they don't need to be very fast, right? And then you've got other ones that, like SPI and I2C, that are used for fairly short haul communication, usually between chips on a circuit board, right? And they're kind of fast. They go up into the megahertz, megabit range, but they're not something that you use to connect your hard drive with. You need something way more expensive and aggressive for that, like SATA, right? So it just depends on, there's a bunch of different trade-offs there. So I mentioned, let's see, there's inter-chip, chip-to-chip, local area network, and then, so some examples here, like with short haul, if you go real expensive, you can get faster, especially for short haul. Longer haul systems like USB and SATA, they're around 500 megabytes per second per channel. And then you have these other ones that are short haul, but they're low speed because they're designed to be cheap. And those are the ones that we're focusing on, the kind of Arduino-based stuff. Okay, so there's a couple different properties that you can have. So these communication channels, you might have covered this in 212 a little bit. They can be synchronous or asynchronous. That's one of the kind of the top level delineations between interface protocols. The difference here is that asynchronous has no clock. There's no clock as part of the channel. And by the way, when I say channel, what I mean by channel is channels are usually multiple wires that work together to create a protocol, right? And so, like for example, a DRAM channel has maybe 200 or so wires as part of it, right? That includes the address wire, the data wire, and all the row access strobe, column access strobe, clock enable, and all that other stuff, right? So anyway, an asynchronous has no clock as part of the channel, and so there has to be some other mechanism for the sender and the receiver to synchronize each other. Right? Now there's various ways that can happen. In the case of UART, you basically just have them both agree ahead of time what the clock rate is, and then both of them generate their own clocks, and they just hope that they sync up, which doesn't always happen, right? You just cross. But because UART is so slow, the very long bit times allow for a big margin of error there, right? But in the case of PCI Express is also asynchronous. There's no clock. In that case, the way they handle that is they use 10-bit, 8-bit encoding, or they use 66-bit, 64-bit encoding, where they take all the words that they send out and they encode those words with more bits than they actually require, right? So you have to send 8 bits out, send 10 instead. Use a 10-bit code word to represent 8 bits. And that coding scheme is designed specifically to maximize the number of data transitions inside those code words. Right? Because what you don't want is like sending all zeros for a while and then you just have a flat line, right? If you send all zeros on an encoded channel, you're still going to get some flipping in there, right? That's what the encoding is designed to do. Then, at the receiving end, they use a phase lock loop, which is an analog circuit, to extract the clock from the data. So you can look at the data and you can figure out, using an analog circuit, what the clock signal was that generated that data. So you basically embed the clock in the data, and that's another way to do asynchronous, right? Now on the other hand, a synchronous channel just has the clock right there. So that way usually the sender is generating the clock, right? Whoever initiates the transaction generates the clock, and then the other end, the receiver, the other end of the connection, whoever's being addressed by the communication, would use that clock signal to read the bits being sent by the receiver, right? So, in this class we use SPI, I2C, and JTAG. Those are all synchronous. There's a clock, and then we're going to talk here about UART, which is an asynchronous. Okay, so the first protocol we're going to talk about is SPI. So SPI is Serial Peripheral Interface. Let me get through some of this, and then we'll switch over. Angela wants to talk too. So SPI is. First off, have any of you heard of SPI? And so if you do any kind of building stuff with low cost, if you ever build hardware, you probably use SPI. It's a really cheap interface protocol. It's and one nice thing about it is I believe it is it's not a licensed protocol. It's you can use it for free. You don't have to worry about licensing it. But it's very simple, and it is a serial protocol, which means it sends one bit at a time through the channel. Right? Most of these protocols are serial. Some of the on-chip ones, like AXI, that we're going to talk about, is a parallel protocol where you send whole words across in one clock cycle, whereas a serial protocol is one bit per clock cycle. Right? So it's a serial protocol, and it is a synchronous protocol, and it's bidirectional. Right? So right there, just from that information, you can tell that there's got to be at least 3 bits involved here, right? Three wires in the channel. There's a clock, there's a bit going one way, and there's a bit going the other way, right? So there's 3 wires that comprise the channel right there. And there's a 4th one too, called slave select, that is used to basically activate the channel, turns the channel on. It distinguishes between the channel being idle and the channel being active, right? So those are the 4 connections, right? Clock, data one way, data the other way, and then the turn on signal, right? Okay, so SPI is a master-slave style interface where you have a peripheral that that's designated the master in the sense that it's the only one that can initiate communication, and the slaves are the endpoints, and they're the ones that respond to requests for communication by the master. So SPI is clearly designed to be something used like in a sort of a programmed I/O style environment where I've got a CPU who's the master and the peripherals are the slaves. They're the ones that you're doing programmed I/O transactions with. Okay, now SPI has some weird quirks to it though. Okay, so let me back up here. So you've got a clock called S clock. Not always called S clock. Sometimes you read document and they change the names of these, but these are common names, right? But these aren't always what they use. Sometimes they'll just call it clock or CK or whatever. But S clock stands for serial clock or SPI clock. I don't really know what the S is. I guess, yeah, one of the two. So there's a clock of some kind. Then there's MOSI, which stands for master out, slave in. So this is the outgoing bits. MOSI is used for the master to send data to the slave, and then MISO is for the back channel, the opposite. Data flows the opposite direction back to the master, and MISO that's master in, slave out. And then SS is slave select, which is basically it turns on the channel, right? Now, outside of active transmissions, the clock is idle. The clock doesn't toggle. Well, why is that? Don't know. I think it's to save power. Like if you're not transferring bits, why toggle the clock? I guess that's the idea there, right? So unless you've got an active communication, the clock is just flat line, right? And then the SS signal is the turn on signal. So you would naturally expect, if that's high, that must mean I'm doing something, and if it's low, I'm not doing something. But no, it's active low, which is done just to be confusing, I think. So SS, when it's logic high, when it's high, that means there's nothing going on. The channel is idle. And when it's logic 0, it means that we've got a transaction happening. Okay? So, does it make sense? You guys with me? So 2 points here. Remember, the clock is idle and slave select is active low. Okay? Now, the way that SPI was originally envisioned to work, but in practice this is not actually how it does work, at least in my experience. It was supposed to be a shift register. So the idea is that when you initiate a transaction, the master will send out a word and the slave will send out a word at the same time, right? And they'll swap, right? So you could think of this as having, and because it's serial, it's 1 bit at a time, you could think of it as a shift register. Now you guys might not have heard the word shift register. Shift register is when you have D flip-flops that are connected in series. Just one D flip-flop has an output that goes into the input of the next, and so on. And so what will happen in that situation is when you clock it, the bits will move one position. Every bit will move down by 1 flip-flop, right? You have a shift, a 1-bit shift per clock, right? So the way that MOSI was envisioned was, I'm going to put all the master bits in a shift register, and then between the master and slave there'll be MOSI, and between the slave and the master there'll be MISO. And so I'm going to spend if I have an 8-bit register here and an 8-bit register here, in 8 cycles I will have shift everything out of master into the slave and everything out of the slave into the master. But it's going to take 8 cycles. It's going to take 1 clock cycle, 1 bus clock cycle per bit, right? And you might say, well, why is that shocking? Well, the problem is that this actually doesn't work for programmed I/O, because the way, as you guys remember, in programmed I/O, I have to send the address out before I do the data part, right? I can't do this swap, because this swap implies that I know which registers I'm exchanging before the transaction even begins, which is absurd. I don't know, there's no way to know that, right? Right? So no one actually uses this model in practice, this shift register model. Now, ironically, JTAG does use this model, and it's a very similar protocol. That's the way that, and you might say, why are you throwing this stuff out to confuse them? The JTAG is when you configure the FPGAs, you use JTAG, and it's also a serial bit shift protocol, and you shift all the bits all the way through the FPGA. And in JTAG actually does work that way. It's designed to work that way. But SPI, it doesn't usually, most peripherals don't do this shift. What ends up happening in practice is the first shift you do is only to send data from the master to the slave, and the slave sends back garbage, right? That you just ignore, right? But I want to distinguish here between this 8 cycles where you do this exchange is called an exchange, right? If I want to then do an actual programmed I/O operation where I send an address over to the master and I ignore whatever, or I send an address rather to the slave and I ignore whatever it sends back, that has another term, that would be part of a transaction. Okay, so I'll talk more about that here in a second. Okay, so see how we doing on time. Yeah, give me a few more minutes. I just want to make sure I want to make sure I get these points across because these are super confusing. So SPI has, you might say, well, that all seems pretty straightforward, right? Okay, so the way this works is everything is driven by the master. The master drives the clock and the slave select and MOSI. And the only thing it gets back from the slave is MISO. It's a feedback signal, right? So if the master wants to send a transaction, it activates slave select, drives the clock, 8 cycles later it does its exchange, right? Pretty straightforward. The problem is, and that is straightforward, except they throw a little bit of a monkey wrench in here. SPI has 4 different, what they call timing modes, that have to do with the actual alignment of the edges during the transaction. And if the timing mode, if the master and the slave are in disagreement about what timing mode is being used, then you'll get like a 1-bit error all the time with these transactions. So this is a subtlety that's kind of annoying, because if you buy an Arduino and you buy a peripheral like a temperature sensor and you want to make a temperature like a thermometer, You connect them together with SPI, and the Arduino, you have to tell the Arduino code what timing mode that thermometer is using. And there's no way to know that, of course, unless you like read the manual for the thermometer, which like guys like me never do. We just guess, right? So like, but that's something that has to be agreed upon ahead of time, right? They have to be in agreement on this timing mode. So the timing mode, there's 2 bits associated with the timing mode. That's why there's 4 different timing modes, because if you have 2 bits, there's 4 different combinations of values. The first one is called C-pole, which stands for clock polarity. And this one is a little simpler than the other one. C-pole is just refers to what the clock signal is when the channel is idle. So remember I told you that the clock is idle when there's no transactions going on, right? The clock is just a flat line. I don't know why. I guess it's to save power, right? But that clock state can either be high or low when it's idle. And that's what C-pole defines. If C-pole is 0, that means the clock is idling at 0. And when C-pole is 1, it means the clock is idling at 1, right? Now, why couldn't they just standardize that? Unclear. I don't know. I think this all was maybe born out of some confusion.
I think it's back dependency. So there are a lot of devices on the market which use different mode, so you cannot standardize them because they are already there.
Right, but I2C, it's standardized, everyone follows the standard. PCI, everything is standardized, everyone follows the standard. USB, standardized, everyone follows the standard. SPI is, you got to customize it because not everyone speaks exactly the same dialect here, right? So you can think of this as a dialect of SPI, right? The other option is CFA, which stands for clock phase. Now this one is the one that's a little bit more confusing. So CFA defines from so think of from the slave point of view. Okay, so the slave is seeing data come in. When data is read, it's latched, it's sampled in a flip-flop. Now I don't know, did you guys cover flip-flops in 211? So flip-flops are these memory elements, right? And they are, there's flip-flops and there's latches. The difference between flip-flops and latches is flip-flops are edge sensitive. So they capture data on either the rising or the falling edge of a clock, right? And the latches are level sensitive. But no one uses latches, everyone uses flip-flops, right? So, and so with an SPI channel, you're going to use flip-flops too. And those flip-flops are sampling the data on a clock edge. Make sense? The question is what clock edge? Rising edge or falling edge, right? CFA doesn't actually define that. It doesn't tell you rising edge or falling edge. It tells you whether you want to read data on the first clock edge, right, or the second clock edge. Now you might say, well, first or second, how do I know which one's rising, which one's falling? Well, that depends on C-pole, right? So in other words, if C-pole is 0, the first edge of the clock will naturally be a rising edge because it starts at 0, it goes to 1, right? If C-pole is 1, the first edge of the clock will be a falling edge, right? Now then, if you take that and you combine that with CFA, CFA will then tell you whether you're going to read on the first edge or the second edge during the transaction or during the exchange. Now you might say, well, first or second, relative to what? Relative to the slave select. The slave select is what defines the beginning of the transaction, and based on that starting point, you're either going to read on the first edge or the second edge of the clock, which may be a rising edge or a falling edge, depending on the value of C-pole. That's why this is super confusing, unnecessarily confusing, right? Okay, so hold on a second.
I can do some examples to clarify that.
Yes, let me get to that, and I'll let you handle the. I'll let you handle the examples. I think. Oh yeah, actually, yeah, those examples are right here. Okay, so Angela will talk about. We'll go through some examples.
So maybe if you go to the first slide, just to clarify. So we have clock equals at 0. If it's 0, 1, 1. Pretty straightforward. And if 0 is first clock age, if 1 is the second clock age, you will need it in the next slide. So here is an example where C-pole is 0 and CFA is 0. Remember, 0 means 0. So basically, your clock idles at 0. And CFA means that you read in the first clock age. So here you have chip select or slave select. If it's high, you don't care, you doesn't read, but at the moment when it goes low, its chip is selected. So that is the moment when you start your transaction. So here clock, SPI is 0. It means that clock idles at 0, and CFR is 0. It means that you read in the first clock age. So here's the first clock age, and you basically read. Now on the half of clock age, signal is set, so you can read it again on the next clock age. And next slide, you can have again 0, 0, 0, 1. Don't look at it yet. Let's look at first two examples first. So basically, both of them have SPI 0. It means that your clock idles at 0. Now, the difference
It's initially 0, right? You look at the beginning. What is clock at the very beginning of the timing diagram? Oh, one more thing. Oh, sorry. So we kind of stepped on this a little bit. So let me just introduce these. These are timing diagrams. Have you guys ever seen these before? Okay, so a timing diagram, just so everyone's on the same page. This is a plot where the horizontal axis is time, and the vertical axis is, in this case, they're just binary signals. So if you're high, it's a 1. If you're low, it's a 0, right? Now you might say, what's the dotted lines for? The dotted lines are just a way to establish a correspondence between different signals in here. So there's vertical dotted lines, so I can see, oh, okay, the dotted line, at this point, like at this moment in time, this signal is 0, and this one is in a state of transition from 0 to 1, right? If you didn't have the dotted lines, it might be confusing as to what's going on at one moment of time, because one moment of time is a vertical slice up through the time axis, right? Okay, go ahead.
Yeah, so basically the difference is in CFR. So basically it says that here you write in the first clock age or read, and there you read the write on the second clock age. And indeed, here the signal is established, and the first clock age you basically can read. The signals are stabilized, so you don't get erroneous values, and you can read. Similarly, here second clock age you read second bit, third clock age you read third bit, and so on. So here you read or write on the first clock age. Here, when CFR is 1, the first clock age here, it's not established. You see those gray things. But on the second clock age, you basically can read it. Signals are established. And here, same thing, but now they have SPI equals 1. Basically, it means that the clock is inverted. So if here you had 0 as your idle state here of the clock, here you have 1. So basically, that's the same. The only difference is that here and here clocks are inverted. And again, SPI 0 means that you read the first age, SPI 1 means you read or write on the second age. So here transition to the low, first transition to the low, you read it. Second transition, read. And here you wait until you get transition of the next clock age and read or write on the next clock age. So basically, this is a little bit early, that is a little bit late. It's half clock cycle on the shift, the difference between the two. And here, okay, here's an example to you guys. We will define terminology later, but we have SPI exchange and SPI transaction. Basically, SPI exchange is the exchange of 1 byte. SPI transaction, it can be multiple bytes. But here we have SPI exchange of 1 byte, 8 bits, and anybody tell what would be the value you read? So you have SPI 1s, it means that your idle clock is 1, and SPI 1, it means that you read on the second age. Okay, so anyone, where we should start? Clock, right? Okay, which of the clock is either 1 or 0? 1, right. So here, then what SPI tells which clock cycle we should read? At one? Second one. Second one. Okay, so we have first, we just omit it and read on the second one. Just when these dots are. Well, it's just coincidence here, but you can read here.
Well, hold on one second. I want to add something to that. So if we get this wrong, though, right? Let's say the slave is set up for CIFA 0, and the master is using CIFA 1, right? What happens in that case? What would happen? Well, the slave would read on the first edge, right? And then which is a falling edge, and then every falling edge, well, for the next, in this case, 8 falling edges, right? Because there's 8 bits. What would happen if it did that? Yes?
It's kind of ambiguous which state the line is on.
Yeah, exactly. When it reads the data is also changing on that same edge, right? So ideally, you want to read the data on the opposite edge in which the data is changing, right? So that way, when you read the data, and Angela mentioned this, but she didn't emphasize it. She said the data is stable. What that means is that the data had been set up a half clock cycle earlier and is not going to change until a half clock cycle later. And so in a flip-flop, you have this thing called setup and hold time. You have to have the data established on the input of the flip-flop for the setup time, and you have to hold it for the hold time relative to the clock edge, right? So what that means is that this allows us to have the data set up one half cycle earlier, and it's held for 1 cycle later. If you violate that and you try to read the data on the same edge the data is changing, the risk there is you violate setup and hold time on your flip-flop, and that causes the flip-flops to become metastable. They go into metastability, which means that the flip-flops will sample a halfway signal between 0 and 1. Now, they'll eventually correct themselves, but in the meantime, you're going to potentially get some corrupted data during that time. Does that make sense? So the objective is whenever you look at the edge of the clock, the data should be read a half a cycle after the data should be read a half a cycle after the data changes, which should also then correspond to the clock edge, right? So you don't actually, if I hadn't labeled this, I didn't even have to label C pull equals 1 and CIFA equals 1 because you can figure it out from the timing diagram. You first of all know that C pull is 1. You just look at whatever the clock starts out as. That answers that question. And for CIFA, you can figure that out by looking at when the data is changing relative to the clock. The data is obviously changing on the falling edge of the clock, and therefore you ought to be reading on the rising edge. And if you look at the rising edge is the second clock edge, so you know that CIFA must have been 1, right? So when you should read it, right. Now again, if you set it up wrong, you're going to get metastability and you're going to get corrupted bits.
But you might not know, but you can get those timing diagrams if you have oscilloscope with you. If you don't, go to data sheet, read what CIFA is, and then send.
Right, yeah, I'm sorry. Yeah, that's a good point. I'm assuming that you that I say you can figure it out with the timing diagram, which is in this class. I'm going to give you the timing diagrams, but in practice, yeah, you'd need an oscilloscope to actually see it. That's a good point.
So basically, let's check. So we had here 1, we had here 0, we had here 1, 1, 0, 1, 0, 1. Correct.
Now in this case, I put the dotted lines on the transitions. Why did I do that? Because I wanted to show the time between my 2 red dotted lines is the up or down that you're reading, right? But another way you could read this is you could draw a line from the rising edge of the clock down to what the state of the signal was using the dotted lines that are already on there. It's up to you what's easiest for you to read it.
Okay, now we have here CIFA 0, CIFA 0. Don't look at this yet. If you can, I doubt you can, but if you can. And just tell me, if CIFA is 0, what is the idle clock state? 0. Remember, 0, 0, 1, 1. And if CIFA 0, what clock you should read? First or second?
First.
So first or second?
First.
Okay. So here we have 0 established, chip select, and then first rising edge from idle to 1. So you read here. So see, in previous example, we found out that we actually read on those dotted lines. In this example, the read should be performed in between. So it's just coincidence. Now let's check. Okay, so here you got 1, here you got 0, 1, 0, 0, 0, 1, 1.
So because it said master to slave, use MOSI. If I had said slave to master, it'd be MISO.
Yeah. And also, most significant bit first, it means that you have 1 to 2 to the 7th plus 0 to 2 to the 6th, 1 to 2 to the 5th, and so on. So basically, this has the biggest power of 2, and this one is just 1 here. That is why you get even number.
Yeah, that one's labeled most significant bit first, meaning that the first bit transmitted, meaning first to the left of the timing diagram, is also to the left of the value because it's MSB first. I don't think SPI defines that.
Yeah,
So you could have a situation where you have a peripheral expecting least significant bit first. Although I think in most cases it's MSB first.
In any case, you just go to datasheet and it should be all there.
Yeah, but it's an option, and it almost comprises another set of timing modes. Like you got to know CPOL, CFA, and whether it's MSB or LSB first. But I think in most cases it's MSB first. But you should confirm that.
Well, sometimes they have like a 5-bit address, and basically you just have send 3 zeros and then you set address. So ideally, you just have you send bits. If you want to write your own dialect of MOSI, you can do it. It's just about sending bits. How to interpret these bits is up to, well, you as a manufacturer or you as a designer. And again, I promised you that we'll go to terminology. So we are here. SPI exchange is in 8 clock cycles. Master sends 8 bits to slave, and slave sends 8 bits to master. So basically one exchange. And transaction is all exchanges that occur while slave select is 0. So basically, you have one transaction of 8 bits, SPI exchange, and transaction can be one SPI exchange or can be multiple SPI exchanges. So that is the difference. And here, master can read data from slave, request the data, and master can write data to slave. Well, in any case, since master is master, it initiates the transaction. But the purpose for that initiation can be or read or write. Well, probably not anything else. So we have, if it read, first we need to notify slave which register or what data we want to get from it. So first byte sent is address and the flag. And slave, sends whatever it sends is not important, usually just set to 0. Byte 2 is basically, in byte 1, master told slave what he wants from it, and then byte 2, master sends like nothing, and slave basically responds to that request. So get content on that register or whatever you requested. Write is similar, so master sends the address and flags to let the slave know where master wants to write. And on byte 2, slave, the difference would be here. So slave sends nothing, but master actually sends the data which it wants to write to the slave.
Now, let me just expand on that a little bit. So I mentioned this earlier, I alluded to this, where SPI is set up for this. I think originally the idea was to do an exchange, right? Like, so I send you a byte, you send me a byte, we're done, right? But the problem is that doesn't work according to the programmed I/O model. The programmed I/O model is the master is going to send an address first, right? And you might say, why? Because generally speaking, the peripherals are going to have more than one register that you can address, right?
At least configure and data.
Yeah, they have like for example, if you have a good example of this is when we originally designed this course, we're going to have you attach a little screen like to the Arduino, and you would put images on the screen through SPI. So you literally would have to tell it what pixel you want to light up on the screen and what color you wanted to make it, right? So there's all these addresses on the peripheral, right? So you have to send an address to read or to write. SPI is fundamentally not capable of doing that using just one exchange, right? So the idea of a transaction is you say, okay, that's fine, I'll use multiple exchanges. I'll make a transaction where the slave select is low, or asserted, I should say, across multiple exchanges. The first exchange will just be the master to send the address to the slave, and the slave has to send something back. It's got to, but it's going to send back random garbage, right? Because whatever it sends back, the master just ignores, right? Then in the second exchange, the rules there, either MISO or just like in the first exchange, MOSI was the address, MISO was a don't care, right? In the second exchange, the MISO and MOSI rules will depend on whether it was originally a read or a write. So if it was a write, then once again, MOSI sends the data, and once again, MISO sends back a don't care garbage value, right? Because basically the second exchange, the first exchange is the address, second exchange is the data you want to write. But on a read, the second exchange is a way for the slave to send the result, the read value back to the master, in which case MISO is being used and MOSI is going to send a garbage don't care value, right? So basically what that means is if you do this type of transaction, one of the two bits in the channel is always going to be unused. You basically have 50% utilization of your data bits because you're only going to use MISO or MOSI. You're never going to be using them both at the same time, which is what SPI was designed to do, was to use them at the same time, bidirectional. But in fact, the transactions don't call for a bidirectional protocol. They call for something where in one exchange you send the address and the second exchange you send the data one way, right? So that's the issue. That's why it's a little weird. You might say, why am I putting two wires down here if only one of them's ever used? Unclear.
So basically,
Right.
that's some design which is not properly designed, or maybe some very good design. But ideally, you can utilize it. For example, if you have a next transaction slave response to the previous, then you can fully utilize it bidirectionally. But people usually don't do this.
Yeah, you could. It's up to you. Like you could use a trick to try to exploit the extra bandwidth that's not being used. But generally speaking, that's not done. However, the reason I'm emphasizing this is because the next protocol that we're going to look at, I2C, fixes that problem.
Yeah.
Right? But SPI has this problem of low utilization of the wires in the channel because of this transaction.
Okay, so let's do read operation. Chip select. Again, here we don't say which C4 because you will anyways see it from the data sheet or see it from the timing diagram. But in this case, we only focus on clarifying how to read and how to write. So you can have, again, it's in data sheet. It may be different. It can be least significant bit or whatever, but most time you get first most significant bit indicates read or write, and then you get address. And here, if it's read operation, slave should output on the next 8-bit output you data. And write, some reason, yeah. And write operation, as you can see, again very similar. You have first bit indicating read or write, then you get address where you want to write it, and again here read is without bar and write with bar. Basically, if it's 1, then it's read. If it's 0, then it's write. And then you have data address where you want to read, and then you have data output.
Okay, so real quick, this is now starting to look like a network protocol a little bit, because the first exchange, the first exchange being the first 8 cycles. So we got 16 cycles now. First 8 cycles is the header. Like the master sends a header packet. You can think of it as a header packet. That header packet includes multiple pieces of information. Read write, which is whether it's a read or write. That's in the most significant bit, bit 7. Then bit 6 is multiple or single, depending on, and we haven't talked about multiple yet, but that's basically how many bytes that you're going to have in the data payload section. And then there are 6 address bits ordered from bit 5 down to 0, so most significant bit first. Now keep in mind though, that this formatting is arbitrary. Different SPI peripherals use different, there's no standard for this in SPI, right? So you could have, we may throw another one at you. Like sometimes we'll give you another format to use for that header packet. But the point is that the first transaction has fields, bit fields in it, And each bit means something different, and it's going to signal something different to the slave, right? So in this case, the first bit is defining what type of transaction it is, and then you've of course got the address in there. And then depending on that read or write bit is going to define which also notice these are different names now. CS instead of slave select, it's chip select CS. Instead of clock, it's SPC. I don't know where that came from. And then instead of MOSI, it's SDI, and instead of MISO, it's SDO. The reason those names are different is because I grabbed that from I actually grabbed that from a data sheet for an actual peripheral, and they just happen to use different names. But that's why I said the names are not locked in stone, but you should recognize, you should be able to recognize what the purpose of each of those is.
Yeah, for example, if you go to Wikipedia page, instead of master, it uses term main, and instead of slave, it uses term sub.
Yes. Oh, yeah. I should mention that too. That's a good point. Yes, they're changed. So, master and slave is kind of politically incorrect, right? But although that's I know, but that's historically. I mean, for literally 60 years, that's been the terminology. And then, in this day and age, they're like, that might offend someone. So they are changing those terminologies. You'll notice that some of the documents will actually use the term controller and subordinate, right? So controller is the master, subordinate is the slave. That kind of makes sense because usually it is the microcontroller that's the master, but I would prefer that the slave be called like peripheral or endpoint or something, but they call it subordinate, which to me is arguably just as offensive, I think, as slave, right? And then what was the terminology you said?
Main and sub.
Main and sub, that's another one. So you're going to have to get used to being able to swap out some of the terminology, like the signal names and these roles. You're going to have to be able to be adaptive there, flexible, because sometimes they change this stuff.
And I would prefer master and slave because it's well used in most of the data sheets. Okay. So we have also, why you have Professor Baker, there's some problem.
Oh, that's okay. You got to switch the slideshow. Boop, boop. There we go. There you go. There and there.
Yeah. Okay. So we have write operation, and again, you don't see slave output because it don't carry on all two bytes because you have write. So first read or write, then you have address, single or multiple. We'll explain later, and the data which you actually want to write to the slave. Now.
Notice one of the lines is missing. Because it's a write, we only use MOSI. MISO doesn't get used, so it's not even shown.
What did you get out from
just click there. There you go. You got it.
Now, no.
No, you had it.
It doesn't. Oh, yeah, no. Okay. So now we have example of SPI transaction, and again, SIPL 1, SIFA 0. SIPL 1, it's 0 or 1, idle clock? 1. SIFA 1, first? Second. Okay, good. Most significant bit, it's just when you read. So chip select 0. From now on, we have transaction. Then we have read-write flag storing the most significant bit of the first byte transaction transmitted from the master to slave. So we have clock. We have to read on the second edge. So here first, second edge, and we get on first significant bit. We got read or write flag. So. Assuming write is 1, if it's write, we say to this bit 1. If it's read, we set to this bit 0. This bar actually indicates that 0 would be true, right? So if we read here on the second clock cycle, and we got first transaction, so what would be the read or write flag in this transaction? What would be the value of the read or write flag? Its most significant bit, the very first thing you read, and okay, let's phrase it other way. Who sends the read or write bit? Who controls all transaction? Master. So which line you should look for? MOSI. Now, what is the first bit read from MOSI? 1. So what is it? So we reading or we writing? Writing. Okay.
And you can also kind of tell if you look at the miso. Notice the miso is just a flatliner the whole time.
Don't give them hints, Professor Bakers. Okay. So we have one. Well, you can see it, and you have this first exchange. So it's right. So you read this right, and at that address, and you read this data to that address. Okay, now, yeah.
Yeah, so this is just showing the fields. DC stands for don't care. So we have a don't care on the first exchange bits 6 and 5, or don't cares because they're not part of the header, packet, field, whatever fields. Don't care is MISO or all don't cares because it's a write. So it's just send the address, send the data, nothing comes back from the slave.
Yeah, and we have these two don't care bits in MOSI because the address bit here, for example, 5 bits. So you just don't need those two fields. Yeah. Okay. So yeah, must write value B5 to address 8. Now, as part of the, how much time we have?
We're just about out.
Okay.
I'm trying to. Yeah,
So,
yeah we're out.
Yeah.
We can end it here.
I just want to go to lab 1.
Oh no, it's okay. We'll assign lab 1 next
Okay,
time.
okay.
We'll do that.
So probably I should let you go, and hopefully we will finish it on Thursday, and I'll tell you what is lab 1, and we start in lab 1.
We have a quiz on Dropbox too. You have a week to take it. Thank.
You said it was due the